All right, so now what we're going to do is, now that we've defined a little bit about internal energy and entropy, we're going to combine entropy and enthalpy to describe spontaneous or non-spontaneous reactions by calculating what's called the Gibbs free energy, but we'll do that later. So now let's kind of look at the play between enthalpy and entropy. Let's just look at something really simple, like the melting of ice. Now remember, for delta H is negative when it's exothermic and positive when it's endothermic. We know that. For delta S, plus is more randomness or more disorder. Negative is less randomness or less disorder, or I would say more order. Okay. Now, when I melt something, I have to put energy in. It takes energy, and just think about melting a candle wax. Got to put energy in, so that is an endothermic, is positive. And when I go up the cooling curve, if I melt, I'm going from a more ordered state to a less ordered state, because the liquid, the particles can move around more than they could in the solid. Therefore, it's more random, and that's positive. Freezing is going the opposite direction. I'm getting energy out, so it's an exothermic process. And in this case, I'm getting less random, or I am getting more order, so entropy is negative. Evaporation. Evaporation is very similar to melting in that it's an endothermic process, and I'm going to more randomness. And condensation, again, is going the opposite direction. That is going to release energy. It is exothermic, and it is less random, and so it will be negative. Okay, so knowing that, so watch your signs here with these. It's going to get kind of, you're going to have three variables in these equations, and they can all be negative or positive, so we're going to have to work with that. Now, what does all this mean? Okay. In terms of entropy, the way we're going to categorize systems where energy increases, and then you can assume that everything else pretty much energy or order or randomness is decreasing. So the entropy of a system increases, or S is positive, when the volume of the gas increases, the temperature increases, the number of molecules increases, the state of matter changes from a solid to a liquid, liquid to a solid, or from a solid to a gas, or I'm going up the steps of a cooling curve. So if I have a cooling curve like that, I'm going up. And a solid dissolves in a solid, so anytime you're dissolving. And you might just want to memorize. You can memorize these, or they are intuitively, we'll talk about them with some specific examples, and you'll see how they work. So, the first thing we want to look at is what happens when we are dissolving something. So I want you to imagine, I'm going to, instead of showing you the picture here, I think we should actually draw it. So let's come down here. And it says, when an ionic solid dissolves in water, the entropy of the ions in the crystal lattice increases, right? Because what's going to happen is I'm going to have this ion, and then the water molecules are going to be attracted through intermolecular forces, ion dipole forces to be exact, right? And we're going to get this interaction, and those water molecules are going to pull the ions from each other. So let's say I have sodium chloride, sodium will be over here, and chloride would be over here, and I would get the hydrogen ion interaction between the chloride, the negative chloride, and the positive dipole on the hydrogen-oxygen bond. So because I'm pulling the ions apart, the entropy of the ions increase. The water molecules, however, are decreasing because now they're less free to move around, right? Because they're stuck with these guys. Where before they were moving around easily, one on top of the other, there was a lot of randomness. Once I pull these ions apart, the water molecules, the randomness actually decreases. Okay, so let's look at a few of these. These are kind of summarize some of the concepts or rules on the other page. All right, this is a phase change. I'm going from solid to liquid. I'm going up the curve, positive. This is a phase change. I'm going down the curve, negative. This is a molecule solid that is now becoming aqueous, which means it's dissolving. The randomness is increasing because it's going from a packed solid to now a solution. Let's look at this one. Now this is interesting. I'm going from a gas, two gases, to a solid, and I'm going from 2 particles to 1. So 2 particles to 1, that means my entropy is definitely decreasing. Here I've got 2 gases, but I'm going from 1 particle to 2, so my entropy is going up. Now, according to the third law of thermodynamics, the entropy of a pure crystalline substance at absolute zero is equal to 0. By definition, that is what 0 degree Kelvin means, is that there is no entropy. So when we start using the equations and we have temperature in our equations, we are going to use the Kelvin scale because that will reflect the full scale of 0 to increasing values of entropy.